Hello and welcome to the inaugural lecture for Mathematics for Public Health at the Fields Institute. I'm going to hand you over to Deirdre Haskell, who is our Deputy Director at Fields.
Okay, thank you, Sarah, and welcome again, as Sarah said, to the Fields Institute and to this inaugural lecture for the Mathematics for Public Health program that is a network of universities across Canada to do research and develop an ongoing network for looking at emerging infectious disease modeling. And today's lecture is well, the Fields Institute is, as I'm sure you know, is located in Toronto, Canada. Some of you might even be in Toronto. I'm not quite sure about that. And its mission is to promote fundamental and applied research in the mathematical sciences, understood in the broadest sense. And we do this by bringing people together to facilitate the communication and collaboration that sparks new ideas. And we've traditionally done that in person at the Fields Institute. Nowadays, we're doing it mostly online, but we're looking forward to maybe being able to be in person again in the near future. And maybe that you do not know that the Fields Institute itself is on the traditional lands of the Huron-Wendat, the Seneca, and most recently, the Mississauga of the Credit River. And we acknowledge and express gratitude for the opportunity to live and work on this land. The Fields Institute is funded primarily by the Natural Sciences and Engineering Research Council of Canada and the Ministry of Colleges and Universities of the Province of Ontario, as well as a network of 9 principal sponsoring universities and other sources. So we look forward to having further lectures in this colloquium series of Mathematics for Public Health. And for now, we welcome Henri Berestycki and look forward to his inaugural lecture for this network.
So maybe I can present our distinguished speaker today, and Henri Berestycki from Paris. As you know, he's physically now in Rome today, and Henri is a French mathematician, but he is really globally known for many of his fundamental research in nonlinear partial differential equations and for his fundamental pioneer work in the general area of modeling and in propagation phenomena in particular. Henri is not strange to the Fields Institute. Henri delivered a series of distinguished lectures at the Fields Institute several years ago. And Henri has been holding the chair of mathematical analysis and modeling since 2001 at the ESS. And Henri is also a senior visiting fellow of the Institute of Advanced Studies of Hong Kong University of Science Technology. You know, many honors and recognitions, or I feel outstanding award from Germany, from France. And Henri is an honorable member of the US Academy of Science and Arts and Science. So with that, Henri, it's very pleased to have you here for this inaugural lecture. And it's also very important to have you to start this. You are a member of our Science Advisory Board. Thank you, Henri.
Thank you very much. And welcome to everyone, and bienvenue à tous. Thank you, Sarah. Thank you, Deirdre. Thank you, Hong, for this very kind introduction. I have to say that I'm particularly honored to speak today for this inaugural lecture at the Fields Institute. I have to say that the effort which is undertaken by the Fields Institute to be at the forefront of the mathematical modeling and effort in general for understanding the epidemics and pandemics, in particular in the framework of the COVID-19 pandemic, is truly remarkable. I think that's really, I want to acknowledge this, that we look at the Fields Institute with really great thankfulness for its efforts. And I think it's really quite remarkable. We look at it as an example, you know, aside from being this great mathematical institute, which we know it is. So I would like to give today a sort of review really of, I'm trying to, can you hear me well?
Yes.
Okay, so I'd like to give a survey here of the recent works in epidemiology modeling that involve in different ways diffusion. And in particular, I want to discuss this in the context of the ongoing COVID-19 pandemic. So, let me start with, okay. How do I change page? Okay, so, sorry. Yeah. So here is my plan. I'll first recall the SIR Chemical Model of Epidemiology, the classical framework. Then I'll tell you a little bit about classical work in the framework of spatial spreading. This involves both non-local contagion and model with local diffusion. Then I'll try to talk about 3 different projects I've been involved in recently, just to give an insight on the type of efforts we're doing now. One is the effect of roads. So how epidemics propagate along roads, and this is a model we have introduced and baptized SIRT model. Then I would like to talk to you about the space-time dynamics of COVID-19 in France. So how a model with diffusion on graphs can be useful to understand these dynamics. And lastly, I would like to talk about very recent and ongoing work on dynamical patterns of epidemics. So to start with, I really want to quote this extraordinary opinion by one of the greatest epidemiologists of all times, Sir Ronald Ross, who went to win the Nobel laureate, sorry, there's a mistake, Nobel Prize in Physiology or Medicine in 1902 for its great discovery of how malaria has been transmitted. So you can imagine how this was important, how many millions of lives really he saved. And in 1911, he wrote this: as a matter of fact, all epidemiology, concerned as it is with variation of disease from time to time or from place to place, must be considered mathematically, if it is to be considered at all. So, saying that you look at variations of disease from time to time or from place to place really invites us to introduce space and time and introduce how things diffuse. You know, time to time, place to place is really the definition of diffusion equations. And so I like to place this talk under the auspices of this great visionary thought of Ronald Ross of 1911. And okay, so let me start with the famous the SIR Chemical model. You all know, I think, about this, but I would like to just have a quick review, just to set the definitions in a clear way. By the way, I like to use some paintings illustrations because probably epidemics is one of the things that has attracted most painters of the ancient times, and really every great painter painted some episode of epidemics. So here is a painting by Nicolas Poussin, which is at the Louvre in Paris. So Carmack and McKendrick were not mathematicians. They were a doctor and a chemist, and they were influenced by early work of Ronald Ross, the same one I just quoted, was the discoverer of malaria transmission. And basically, Ross understood that one needed a mathematical model for transmission. And he worked closely with someone whose name has been forgotten, unfortunately, Hilda Hudson. As many great discoveries of the past, a woman was involved there and whose role was neglected in the following years. Hilda Hudson was a remarkable person, quite a remarkable person. In fact, she was the first woman to speak at the International Mathematical Congress. She had a position in Cambridge, and later went on to work in industry. She had very wide, she started in geometry and in arithmetics and had a very, very wide range of interest. And I think it's fair today to try to, even though it's hard to reconstruct exactly or the role she played, but I think it's fair to place her again in this. Ronald Ross, by the way, is also quite an interesting fellow because he was also a writer, a poet. He wrote theater, and he really loved mathematics. So you can understand that. So hence his sentence and his efforts to find early models of epidemiology. Now, among the precursors of this, there's a medical doctor from the Bernoulli lineage. And as I said, Ronald Ross, Hilda Hudson was the first on introduced mathematical models. And one of the main aspects of this all was the idea of law of mass action, as we'll see. And this was, in particular, Lotka from Lotka-Volterra also had the ideas that this should play a role, and I'll point out to you where it comes into play. But this was born from a circle of ideas from chemistry and how things spread in general, what the kinetics of certain phenomena, which was the law of mass action. So Kermack and McKendrick came up with SIR compartment models in epidemiology. These are really a class of models, and they had an early success, which was quite remarkable, and therefore it really became one of the fundamental systems, and it's used overall. It's used in many different fields. I won't have time to touch upon this, but it's also used in social sciences quite a bit on how things spread, rumors or tastes or opinion, fads, and so on, or adoption of technologies, how this spread is. Many people have been using epidemiological model of the SIR type. So the SIR type, as you know, involves considering the population is divided into 3 compartments: the susceptible, the ones who are infected or infectious, and the one who become recovered or removed because they die, for instance. And this happens with a certain rate beta IS. I is the number of infected, S the number of susceptibles. And this rate is exactly what I call the law of mass action. It's this product, the fact that it's quadratic in this IS is because it gives us this law of mass action. So this is a basic model. So it says, if you translate into equation the diagram I just showed you, it says that the variation of S is minus beta SI, product. So S is depleted by the epidemic. I gains from the epidemic, but the same what S loses, so it's plus beta SI. But people eventually are removed or cured or die, and this happens with a rate gamma. 1 over gamma is typically a length of the disease. The length in time, the duration of the disease. And so R is removed. So you see, R is just obtained from the other quantities. So we usually write the system just for S and I and forget about R. And the typical behavior of such an epidemic in SIR model is that you see S just decreases all the time until it reaches what is now called a herd immunity. It doesn't go to 0. So there's, like in the picture I show you, if 20%, if 80% of people are removed or immune, then the epidemics just stop spreading. That's a herd immunity. And you see in red the number of infections, so the incidence rate, if you want, and the prevalence rate rather, and I is recovered here. Sorry, R is recovered, which is the integral of I. I is in red. Okay. So as you know, there's a basic reproduction number that says whether the epidemic spread or doesn't spread. So this number R0, I'll come back to this. And just let me point out that there is a very special case for general class proposed by Kermack and McKendrick. And as I told you, there's a law of mass action here for the term SI. And there are many variants and extensions which have been used and are used all the time by people who do modeling, practical modeling. So here is one when you introduce a new class of exposed. So before you become infectious, you're exposed. And if you do that, so you write the diagram you will write. And here you can even do the difference. You can differentiate it between the people who are removed between ones who are protected and ones who die. And here is another one. You can become more and more precise. People are diagnosed, people are not diagnosed, people have symptoms, without symptoms, the ones who are healed, the ones who are ailing, critical, not critical, people who die. So all of this, you just write this. It's like a Lego system to write models, in epidemiology. And of course, a lot of the work is to identify the various parameters that come into play. But the basic idea is the same as what I showed you. Now, what about spatial spreading? So spatial spreading, let me start with non-local contagion. It was first introduced by Kendall early on. Kendall has this idea to consider models where he was interested in the spread of rabies in England and looked at the possibilities that fox travel distances. So you can have people at location X infected by people who are at location Y, so long distance contagion. And this involves, instead of having minus SI, you have a certain kernel beta. Instead of having beta constant, you have a certain kernel, beta of X and Y, that says what is the rate of people at X infected by people at Y. So in the previous model, beta was constant, and I didn't depend on Y, so you just have I of T. Here you have this, so now S and I depend on X and T. And you're exactly the same model as before, but except that now you have this term. I don't know if you see the pointer here. Do you see the pointer? So you have this, this term here, which is instead of beta SI, you have beta, S times beta integral of beta times I. So this was Kendall. And he looked at the case of compactly supported beta with beta, depending on the distance. And he had heuristic argument for pandemic threshold theorem and formal argument to describe spreading. I'll just say a word about this. This was later, in 1977, proved with a complete mathematical theory, which is an important step here by Don Aronson, by introducing the cumulative density of at location X of people infected at location X, so the function U. He proved that there's a constant solution. You can identify what's the constant steady solution here. You just have to solve a certain equation here, which involves the integral of S of beta. U star is the unknown here. And if R0, you have R0, which is given by this now. So you see it's integral of beta rather than beta as before. And if R0 is less than or equal to 1, the epidemics just dies out. Whereas if it's bigger than 1, it spreads. And in addition, there is an asymptotic spreading speed, which I call CSIR here. And what this happens that if you look at people who run with a speed C less than CSIR, so inside the sphere which expands with a radius CT, with speed C, if C is smaller than these critical numbers, then you will see around you the maximum number of people, steady state, non-zero steady state of people who have been infected. Whereas if you run faster than the spreading speed here, CSIR, then what you see around you, soon enough, you see people are all, no one has been infected. So this is the spreading speed that Aronson obtained, and it's very much related to works that Aronson-Weinberger, classical work of Aronson-Weinberger for so-called Fisher-KPP equation, Kolmogorov-Petrovsky-Piskunov equation. Now, there have been several works only recently for non-local setting. Still a lot of remains to be understood. One of the main works is due to Romain Ducasse. It's available online for the non-local periodic setting. And but this means that the coefficients are periodic, and you start with an initial data which is also periodic, and then it proves the same thing. Pandemic threshold theorem. It proves the existence of traveling waves. But the question of asymptotic speed of spreading is the same spirit of what I just showed you, even in this periodic setting, which is supposedly easier to deal with than the fully heterogeneous case. This is still an open mathematical problem. There are many interesting and fascinating mathematical and difficult and interesting mathematical problems in this area of epidemiology. Let me just go very quickly over this. Dickman and team wrote papers on some of the original classes of Kermack-McKendrick. So Kermack-McKendrick was more general than the SIR. It involved a model where you keep trace of the age of the infection, tau. So it's like more or less it's analogous to having a population structured by age. So you have integral equations, which are a bit more complicated, and Dickman and team, those are very important milestone works, define the notion of suitable R0. They proved an epidemic threshold. You know, that's always a game in epidemics. One of the main modeling, you really want to understand when the epidemic spread or doesn't spread. And there's been many, many subsequent works of in this direction. So let me tell you now about this SIR model with diffusion, and with diffusion, local diffusion. So if you look at, so instead of thinking of that people can contaminate far out, you just think of a population of individuals where everyone moves with a certain, you know, longer Brownian motion, if you want. So if you do that, and yes, you assume that only the infected move around. I think it makes sense. You can, you know, of course, you could also assume that the susceptible move around, but you know, you think of the susceptible as a kind of ambient data, and so it's the same model as before, exactly the same model as before, except that the infected now depend, and S also, the susceptible depend on T and X. Do not depend only on T, they also depend on space, and the dependence on space is related to this term, d Laplace I, which represents in this equation the effect of moving randomly around for the infected. So this is in some sense the simpler model, the simplest model you can think of that incorporates spatial heterogeneity, spatial movement of the infected. So this is again, in this model you can prove a dynamic threshold theorem, you can prove an asymptotic speed of spreading. And the asymptotic speed of spreading is the same as before. So if you run fast enough, you will escape the epidemic. If not, you will be in a place where the epidemic will go fast at, you know, the highest level. And this, by the way, the paper of Dickman is entitled "Run for Your Life." So it's a very nice title for this. So if you run fast enough, you escape the epidemic. If you run not fast enough, then you are caught in it. So again, so this is this model, which I just showed you. And in this case, it's simpler than in some sense, than the integral, than the local term model, because you can prove it really reduces to the Fisher-KPP equation, and you can use results of Arons and Weinberger of 1976, very classical results in reaction diffusion equation. And you have an asymptotic spreading speed, which is given by this number here, which you have here, CSIR. So it's 2 square root, it's very precise, 2 square root of D alpha. D is a term here of diffusion, tells you how far rather the individuals disperse over unit time. Beta and alpha and S0 come into play with this number R0, same as before. And so if R0 is less than 1, there is no spreading, but if R0 is bigger than 1, then the epidemic spreads spatially. You start, it's another notion really of spreading, it's more natural notion. You start at a point and then it expands spatially with the speed. And this is a definition of what it means, expand spatially with the speed C star. It's summarized by those 2 properties, which are here. There have been many works on this. So many traveling waves are very well known by early work of Kalend and also known in Elias, and again derived from Fisher-KPP equation, and also for systems a little bit more complicated. Also Elias have done that. And in the periodic settings, there's a very nice work by Ducrot and Giletti, who study pulsating traveling waves, and also in this case are able to look at asymptotic speed of expansion. I should point out that here again, if you add diffusion of susceptibles, so if you have really genuinely systems of 2 PDEs, partial differential equations for S and I, then the non-homogeneous setting, including this periodic setting, is still open. So let me tell you, so this was the classical works I wanted to mention, just to give you an idea of the framework. It's a classical framework. And I wanted also to tell you about the other works. But let me now move on to the 3 new recent works I want to tell you about in surveying them in general terms. So the first one is about the effect of roads. So So the effect of propagation of epidemics along roads. Since I'm in Italy here, I like to quote some works from Italian scientists. So in particular, I'm going to quote works from Gatto, which appeared in his collaborators, which appeared in PNAS in 2020. This is what you see here are roads in Italy, basically. This map of Italy, it's truncated to the bottom, but it's, you know, it's this, as it's called, a boot. And what you see as a towns here, you know, this point is Milano, where you have many, this point is Rome. And there are indeed spatial effects which are very important. So let me, to get back to this, let me just show you this map, which is reconstituted data for the Black Death spread in Europe in the middle of the 14th century. So Black Death, what's interesting is that if you look at this picture, you see that it moved spatially to a very well-defined front, moving year after year and invading new territory. So started with the dark brown here, and then moved on with, it started here somewhere, in particular on the continent, started here. That it was really very localized, and then spread in 1348, where all this light green area, then dark green area next year, brown or beige, and so on. It moved just around all the time. So you see that it really moved like a front. It's quite remarkable. Now, of course, you have effect of homogeneities of terrain. You have homogeneities of mountains here somewhere, and so on, forest, mountains, here in particular also. But what's interesting here, if you look at this part here, you see that there was an indentation. It moved faster here. Now, this is the Rhone River that connects Paris, Lyon, and, well, this part connects Marseille and Lyon, but on the main road from Marseille, Lyon, and Paris. And this was a very traveled road. So you see the epidemics traveled faster along the road and spread inwards afterwards. So that's a phenomenon which is very important on how epidemics spread. They really tend to spread along roads. And this is quite an illustration of this. So if you look at the effect of roads more recently in the COVID-19, I like to quote this work by Sebastiani and collaborators, which he has entitled "The Coronavirus Has Traveled on Expressways." It's appeared 2020. And so the argument is a statistical argument, but basically here on this picture, you see all Italian counties. All the Italian counties in Italy, counties are indicated by their main city. So all these are all the main cities of Italy, representing all the main counties. Roughly is the same, you know, all the main Italian counties. Now, if you look at all the counties, among all these counties which I showed you, if you look at the counties where there were a large number, I think more than 1,000, I think 1 per 1,000 incidence rate at some point, you, more than 1 in 1,000, I say. So you obtain these cities which are represented on this right-hand side graph. You see, so it's only a very small portion of the cities on the left that you have there. What is interesting is that those cities are all connected by the main 2 or 3 main expressways you have in Italy. So it's quite remarkable to see that the cities that were infected were high infection rate were actually on the line of expressways. And if you look at these 2 cities here, which are the intersection, these were cities which were particularly badly hit in Italy, and those were more hit than any other one. And you see that they are the intersection. They sit right at the intersection of the 2 express roads. Now, you could claim that this is because expressways connect more important roads, more important cities. But that's not true, because you can compare cities of similar population, similar economic importance, which are not on these expressways and still are on the left-hand diagram, but not on the right-hand side. So this is quite a convincing argument about the effect of roads in the COVID-19 propagation. At least, you know, of course, this is something that's probably relevant in Europe, and I wouldn't claim something like that in the North American continent. But in Europe, where travel by small distance is very important, this is quite remarkably important. So yeah. Okay, so these were counties with more than 1,000 cases. So Gatto and others, his collaborators in his papers of PNAS 2020, took into account the effect of roads, came up with a model. As you see, it's quite a sophisticated model, one of these variations of the SIR model I mentioned before. Had a model where they use the data of how many people travel on each road. They injected this in the model. They obtained this from statistical databases of Italy. And you could see then with the model, you could see also how things travel. So here I think it's data first. So this is where the data, how the epidemics, the lighter, the less, because the darker, the more people were infected. So this is how it traveled from north to south in Italy, basically, okay? This is the proportion. Now, you can now compare this with cities if you have simulation. So this was a simulation that I mentioned before, what I showed you taking into account roads. So here it's at the level of cities. Here it's a simulation at the level of counties. All these are counties. And here is data at the level of counties again. On the right-hand side one is level of data. In between, it's simulation. So compare those two, really. It's the center one and the right-hand side. The other one gives you some also interesting information. So, okay, sorry. So here's what they obtain with the simulation. You see, so that's where it starts. You see the cities, the counties. And you can look on the center and on the right, and you compare simulation and data. It's truly remarkable how you can really get a lot of information from this model, how accurate it is in describing the propagation. And if you look at the level of municipalities here on the left, it's even much more precise. You can really go down and obtain this at the level, very, very detailed level of propagation. So we decided to try to understand within the SIR model without going, can we obtain something theoretically at least as that would account for something like that for an effect of roads. And this is something we did with Jean-Michel Roquejoff from the University of Toulouse, and Luca Rossi was here in Rome, and something that just appeared this year in Bulletin of Mass Biology. So the effect of roads on propagation of epidemics. And the model involves a new, so it's the SIR model with diffusion, but we have now a new compartment, which we call T here. It's a compartment of, sorry. Can you see? Is it okay? Can you see?
We can see it, we can hear it very well.
Okay, so the new compartment is T, traveling infectives on the line. And the idea is that you have S and I do the same thing as before outside of the road, outside of a line. But I contaminates S at a constant rate and it's removed as before. But now we have infectives that move in the domain. So they have local diffusion as in the model I showed you, but you now also have people among the infectives that board trains, if you want, or go on expressways and go out at other places on the expressway. So the line and the plane exchange infectives at constant rates. That's an assumption we made. And we try to understand how we can account for how this plays into the spreading of the disease. So we have now a model with this. It's exactly as before, except now we have two more parameters which are in red here. Mu is mu and nu are transmission rates between the line and half plane and vice versa. And you have a diffusion as before in the domain, but now you have a new diffusion on the road, which I call uppercase cap D. And that's a diffusion on the line. So these are the new parameters, mu, nu, and d. If you write the model with this, and for simplicity, let's write it as when the line is just the border of a half plane, the domain is just a half plane. You would like to simplify things when you want to prove mathematics, but indeed, the goal here is to capture this phenomenon. And you will see that you can adapt it then to practical things. But at least in this mathematical sense, we have exactly as before, those are the equations I wrote to you before with local diffusion in the upper half plane. And now you have the road. On the road, you have the traveling effective, and the traveling effective diffuse with a coefficient capital D, and they gain effectives at a rate mu from the field and lose to the field with a rate mu traveling which go down to the field. And the field, of course, gains the opposite of what the road gains or is equal to what the road loses. And this is translated into this boundary condition, which is what we call a Robin boundary condition, saying that the y derivative of I at the road times d is equal to mu t minus mu I, with a minus sign. Okay, so if we do that, we can introduce cumulatives of both infected in the field and on the road. And if we do that, we end up getting a model which is very close to something we had introduced earlier with Jean-Michel Roquejoffre and Luca Rossi, which was aimed at understanding the enhancement of biological invasion by transportation networks. In fact, here, the same technology with some variations, of course, works to explain how the effect of transportation networks may affect the propagation of epidemics, if you have this type of. So here is the type of system you get here for the cumulative number of t, cumulative number of I, which I call v. F now is this thing you get from integrating once an equation, and you have these equations for u and v, which looks classical, except now you have a source term here, which makes things a little bit more complicated. But nevertheless, we can use our technology, and we prove that there's an R0 under which we go on. If it's below 1, the epidemic will go extinct. If it's above 1, the same as before R0, epidemic will spread, and there is a epidemic. There is a asymptotic speed of spreading, and the main point is that the asymptotic speed of spreading here tells you if you go faster than this on the line, let's say, if you go faster than, or in fact for any x, if you go slower than SIRT, you'll converge to this maximal level, if you want, of U star V star, cumulative number. And if you go smaller, if you run faster rather, then you arrive at the situation, you run for your life, as it were, and you escape the epidemic. Okay? And so you can say also, you can compare this with SIR. SIR without road is a benchmark here. So you want to know whether road can accelerate this phenomenon. And it does accelerate this phenomenon if D is larger than 2D. So let me not go into more details here, but let me just say this. You may have situation when you have the epidemics, let me just draw this conclusion. You may have situation when the epidemics barely propagates. So when R0 is close to 1, we have a situation where you have very close to 1, and the SIR model tells you that it barely propagates. But if the effect of the road is sufficiently large, with this D here, there are some effects here of mu and nu, then this term here can become larger, strictly positive. So in fact, it can have a positive limit. So the product of those two things can have a positive limit. So you may have a situation when CSIR is very small. So if you have no roads, the epidemics barely propagates. While if you inject the effect of road, you may have long distance effect. And I think this is really very telling about how the effect of roads may take you to a situation when the epidemic seems to propagate very slowly, but then all of a sudden you have down the road somewhere far enough, you have something popping up. So that was one of the outcomes, one of the main theoretical outcomes of this study. And we try to apply this to France, really to this same model I just showed you with a team in France. This is Lionel Roch in particular, with whom I've collaborated, and Jean-Michel Lucas and Olivier Bonnefond. And this was taken in Paris last year. So we're working on this, as you can see, observing the measures. And okay, so I'm not going to go into many details. Here there are many questions on how you apply this to real situations. You know, you have segments of roads, so you have to, so segments of roads board boundaries of two domains usually, and you need to introduce a new models. There are lots of mathematical questions, actually fascinating PDE questions about this, which require to be solved. There is some ideas that Roch and Bonnefond had introduced to study the invasion of the mosquito tiger mosquito in France, and which give very good results using this road effect. But here we can do the same. And let me go into details here, but then let me just show you, this is France. And this is France, and we're going to, what you see here are the main expressways in France. I think there are more like 20,000 cars a day in these expressways. And so it's, you forget about most, those are the major expressways in France. And we're going to, we didn't try, this is not realistic, we didn't, but we tried to do something which looked like realistic. It's not, we're not going to calibrate this completely over data for the moment. Just try to understand the effect of roads here. So what you see here in France is where the epidemic started in France. Started in the east region of France, Alsace region or Lorraine, and also north of Paris in the Oise region. So we start with initial data here, which were realistic, and we try to see how, in taking into account the roads, describes you the propagation or not. And this is what you see. So here you see the number, the prevalence rate, number of infected at a given time. So here now is between the lockdowns, two lockdowns, okay? And then there's another second lockdown coming into play. And see the lockdown has the effect of, okay? So let me just say it again. Okay. So this is went fast. So you see, this is epidemics before March 15th, and then the first lockdown comes into play. So it resides, and then lockdown is lifted. It propagates again, and you see it propagates along roads. Now the second confinement. You see the effect of roads, and that's more or less, by the way it looked at that time in France. The southwest part of France was by and large spared. And so here is, if you look at the cumulative number of, you see this thing, the cumulative number tells you, and this again really is quite, so again, first lockdown here, so it doesn't increase much. Now lockdown is lifted, it further expands, and second lockdown comes into play, and you have this. So you see how it's spread in France. Again, as I said, we didn't try to, it's just an illustration that such a model has the ability to be really useful for that. Let me tell you something more applied, more applied on real data, which is something I carried with a team in Avignon, in the team of INRAE, the Ergonomics and Ecology Institute Research in France. And this time I illustrated it with not such a classical painting, if you will forgive me for this. And this team was done with Olivier Bonnefond, Virgile Baudreau, Samuel Souberan, and Lionel Roch. And you can find this in Royal Society Open Science, so it's open access, December 2020, and you can also find it on medRxiv. And this is really, I'm not going to go into many details here, but let me just show you the incidence rate of the first wave in France, how things spread. And so it spread, as I showed you, as I told you before, it spread on the east and the north of Paris, well, in Paris region, in fact, after that. And this is incidence rate, okay? So the incidence rate. And we tried to understand how we could model this. And I'm not going to go into many details, but basically what we do here is a SIR model, except that it's a compartment model for every country. Each county, there are 95 in France. Each county has a certain number of S and a certain number of I, and you look at how the I can affect S, and we do that so there's a graph of counties, okay? And we do that with saying that there is a certain, people of the same county can affect people in the same county, but they can also affect by long distance by traveling. And the traveling here is measured with a certain weight. So you have with a weight here. So you have a graph here. You have propagation on this graph, and you have these weights which are done here. And this has, by the way, this type of function was justified, for instance, in terms of human contacts. For instance, there's a very interesting study of how short time dispersal of banknotes in the US take place. So basically it goes along weights like that. And okay, and also was used in other disease modeling also, type of weights. And I'm not going to go into play, but we really can, using that, we can fit very well at regional scale the epidemic, really quite well. And so let me not go into this, but you can see there's here online, it still is active, I believe, using such a model and other calibration arguments. In this thing, you can see a forecasting, I think for every country, but you can see forecasting of the disease. So it's really quite applied and calibrated and yields very reasonable results. Here you can, by using such a model, you can try to see what's the effect of different strategies. So if you restrict social movement, if you enforce social distancing, or so if you have no restrictions, if you have restrictions on inter-county movement only, or if you restrict only the contact rate, or if you do both, such a form. And as you see, if you don't do anything, then you can measure by extrapolating the number of deaths that is incurred, and this was done. This was done at a certain day, which I don't have here, but this was the forecast. And as you see, since it's a logarithmic scale, the number of deaths you get here by not having these measures is very large. Now, if you enforce only the inter-county movement, you are still diminishing the rate, but you still get the pool in terms of deaths. If you restrict severely the contact rate, then you get the blue curve. But if you do both, then you get the light blue curve, which is really the one that, so you see this effect of just limiting the inter-county movement is not enough. But if you couple it with restricting the social contact, then the result, the outcome is really very strong. I always was wondering whether in France, when the government may have seen, or through maybe intermediate steps, may have seen this study, because that's a measure which was taken in France in this last confinement, where inter-county movement was restricted, was forbidden. And I see, and indeed, it's really had this strong, it was not as strong in terms of social contact, but inter-movement was more restricted. And I think it yielded some effects because of what you see here. So let me just tell you rapidly, I see my time is almost up, about the serum-academic model, about the dynamical patterns of epidemics. So this is joint work with Benoît Desjardins, Bruno Heinz, and Jean-Marc Bourry, very recent work. You can find a paper by us on medRxiv. It appeared on medRxiv. It's under revision for a journal right now, but it appeared on medRxiv. And what we do here, we want to understand how certain dynamical features of epidemics appear. So in particular, we were concerned with the idea of plateau and other dynamical features. So plateau, I like this because everyone talks about plateau. There's recent epidemics, all politicians talk about R, number R, news people talk about R, and all people talk about plateau. Here we have many journals and media here where you say, in Germany here, Zahlen auf einem gewissen Plateau zu halten. Fauci says US coronavirus infections may be plateauing, so there is now even French word is being put to rather severe uses, all plateauing and starting to fall, etc. You know, you have even a French president. Aujourd'hui, nous sommes sur un plateau. So we were concerned about why is there a plateau? In fact, if you look at what I showed you, the type of things I showed you from the SIR model, there are never plateaus. So how come there are plateaus? So plateaus do exist. If you look at this data, for instance, you look at here, number of hospitalized individuals in France in a given period, you see that there is indeed a plateau. And it's not coherent with the SIR, classical SIR model. This is the R model, the R gotten from this site I mentioned to you in RAE. This is the address you can find. And in different countries, and you see you have by and large again a kind of plateau developing, and so to understand this, we relied on the measurements that were taken around the Thau lagoon in France. Thau lagoon is a lagoon here you see, which is between Marseille and Montpellier, near the city of Sète, southwest of France. And there we rely on measurements from wastewater. So wastewater is really a fantastic tool to understand how epidemics happen. In fact, clearly it can be said that it's the only completely objective, if you know how to take into account certain things as rainy periods and other things like that. But basically it's the only thing which is completely objective, is not subject to different medical measures so you really can measure the ongoing epidemics from the wastewater measurements. And these were done in 4 wastewater treatment plants, WWTPs, on this region, using a new method which is called digital PCR, but especially done by this company called IAGE. Now it's called GeoBiomics, and gives quite extraordinary results because it's almost like an experiment. Because of this, it allows to take very precise measurements, more precise than usually. And also you can do them in a quite automated way and for long periods. So we have data for long periods and taken every week. So it's almost like an experiment, really. So that's why I call it the Thau lagoon experiment. And this is what you get. So these are divided 4 cities, 4 treatment plants. They are grouped into 2 pairs. You see, one pair starts here and goes up to a certain level and then goes to a plateau. So the orange and green. The other groups of 2 cities starts later. It starts later. But what you see here is that it goes up and basically the delay of 2 weeks remains constant all the time. And what is really amazing is that it stops when this has already stopped here and already started to go down, the first group, this continues to grow until it reaches the same level. So this tells us a lot of things about the way epidemics go. It tells us that there is something intrinsic here in the dynamics of this. This cannot be related to national social distancing measures, for instance, because it would have affected both groups in the same way. And you can see that one stopped while the other continued. And you can see the plateau effect, a very strong plateau effect. So to understand this, we introduced a new model. We introduced a model with heterogeneous behaviors. And there's a variable A, which has nums with score if you want. And we have a new model where there is heterogeneity and variability of population behavior. So social diffusion, that's a word that John Hong coined, and I think it's an extremely adapted word here. Social diffusion here means that people change their behaviors, not the infected, but we look at the susceptibles and change their behavior. And you now have, instead of having 2 systems of integral equation, you have a system of integral differential equations. You have a heat equation with a non-linear term here, and you have the same here for this equation where you take into account the fact that the beta depends on A. A is the kind of risks that people take. So the higher the A, the more larger the beta. So not everyone has the same risk transmission coefficient beta. It's very natural to take this. And if you do that, so this is what we'd obtain when we calibrate on the Thau lagoon on the set. Here's the set one of them, set we calibrated here. And it gives exactly the type of behavior. We started to do that only here at this date. I'll come back to this in a minute, but the initial phase, but it calibrates and it has, you know, this shoulder type, which is really very characteristic, and this sort of small oscillation that you, and plateau. So plateau, you can obtain plateau provided you take into account social diffusion. By social diffusion means that people change their behaviors from day to day. And by changing the behaviors from day to day, some people were cautious at the beginning, are less cautious the next days. So this is as though you were bringing new victims to the epidemic every day. And that explains why you have a plateau. That's a very natural explanation for why you have a plateau. And you may look at the effect of diffusion. Diffusion should be there, but not too large, because if it's too large, it homogenizes things. So you are back to this no plateau effect. And it's natural, so you have some intermediate region where you have oscillations, you have plateaus, as I showed you here. And this is where you look at the effect of various, the various A's which are responsible. And you see it's a large A that are responsible for the, so smaller number of population, but are responsible for the plateau effect. You may have multiple epidemic rebounds, even if you include, you know, the fact that you go out of a certain, at some point of a certain lockdown, then you may go obtain peaks which are higher than the previous ones. So you obtain these peaks here in such a model. You may also have effects of variance. So you may have maybe on this kind of plateau, and all of a sudden you have a variance and you go to a higher. So all this allows, you can use these models. It's very, I think it's very natural model, very natural class of models to use. So last thing I want to say here is that very recently we understood that this type of models can also be used to account for the initial phase of epidemics. So initial phase of epidemics you see is here, and initially you have small numbers and it goes down rather than going up. And in fact, with a model like what I've presented here slightly, now it's a dual model as it were from the other one, in the sense that it's the I where you look at the differential values, different values of I according to A, and not so much about S. S is fixed, you know, at the beginning of an epidemic, you can consider S of A as fixed. And you can see here that the total number starts by decreasing. So you have a period here where you have latency of the disease. So this explains why, in my view, why in France, for instance, or in Italy, you say people think that there were already COVID-19 patients back in December, even November, some people say, and there is a latency time. So this model explains both plateaus and latency periods. So I think I went over my time already. So this explains the latency period I showed you before. Okay, and so with this, I would like to thank you for your attention, and I'm open to questions, of course.
Thank you, Henry. And maybe first add that when Fields Institute, along with CIM, the ARMS and PINS, to commission this national task force, and then eventually build its network, Mathematics for Public Health, one of the ambitious plan is really to not only deal with the most significant public health issues, but also to elevate to theoretic problem to challenge the advanced mathematics. So I think Henry's lecture really represents the finest example of what the Mathematics Research Institute want to do. And I'm very pleased that Henry is with us today. And any questions or comments? And Deirdre, you raise your hand. You want to start?
I don't think I raised my hand. I think I was saying thank you.
Oh, thank you.
Sorry.
Nisha?
Yes, Professor Henry, it was a really interesting lecture. I have 3 questions. First, when you described all the 2 models, SIR and SIRT, you describe about the speed that C less than or greater than CSIR or CISRT. I was wondering what would be when C is equal to CSIR.
Yeah, that's a good question. it's a mathematical question, I would say, but it's a good question. And so in the Fisher KPP equation, which this is very close to, there is something, so when you are the CSIR, exactly this, if you look at CSIR times T, in fact, you are in the free zone. You run faster than the epidemics. This is related to the fact that there is a shift, so-called logarithmic shift of the front. The front is not exactly located at this critical C times T, but at this C times T minus a constant time logarithm of T. This is called the Branson shift in the KPP, Fisher KPP equation. In this model, it's open. It's a beautiful mathematical problem. We don't know. We believe there should be a shift, but it's not known. And this is open terrain for whoever wants to do it mathematically.
Okay, thank you. And the other thing I wanted to ask that I saw there was differential equations in the model. So I was wondering what numerical method you have used to solve this, and is it a linear equation or nonlinear equation, and how you have discretized the domain, which is the region in your case.
Yeah. So the methods I think are classical, except for the fact, I suppose you are referring to the situation where we look at the effect of roads, right? So the effect of roads, then that's really complicated. So for instance, you can look at the situation which I described with the major expressways, if you want to do that. And then you have certain regions which are, France is separated into different regions. But the difficulty is that you have certain portion of roads bounds both two regions at the same time, and there are triple junctions and so on. So this is a little bit difficult because what I described to you was a case when mathematically, we have to treat the case when the boundary is just on one side. So if we do that, we need to introduce, so this is something, an idea that was introduced by Roque and others, and Bonnefond, I believe, in the study of tiger mosquitoes. We need to double the road. So there's a technique where you look at the road as though separated in two. So each domain has its own road, and then you introduce a penalization term that tells you that the values on the two roads must be close to one another. Okay, so they double the roads. It's doubling the roads. This is not at all understood mathematically. I think it's a very, very beautiful mathematical problems, even in simple cases. I mean, even if you take just one road and two domains, I think it's very natural to look at that, and it should be, but it works, as mathematicians worried when things work in practice, they're worried whether it will work in theory.
True.
Thank you, Nisha.
You had the third question, Nisha? You had the third question?
It has two questions. One was the discretization, and other, I was interested in the method, numerical method you have used.
Okay, the numerical method, I think, is just plain finite element, I think.
Finite element, okay. Thank you.
Henry, I have a scientific question, non-scientific questions. The non-scientific one is the one you have the 2020 painting. Your title is unknown. How did you get the painting?
Looking on the internet.
Yeah.
So I'm not sure. Yeah, maybe there are some rights attached to it, so I'm not quite sure. So I just, obtained it from the internet.
Thank you. The scientific part, I believe you mentioned that the PD model might not necessarily spread road apply to North American, but I believe I remember some study about the vector-borne disease transmission along the corridor of it's Highway 95. I forgot the really show. I don't know if it's from your work or not, but I do believe there are some modern studies.
Yeah. Okay, that's a fascinating topic and it's extremely interesting point you're raising. I just said out of caution that I'm not sure whether it applies to North America because, things when there is very low density along the roads, roads may not be the most, may not be the most adapted tool to understand this. Yet, yet. So and I think you have already seen some cases in North American for spreading of certain diseases in birds. I believe you have seen also the effect of roads, of lines. So, so yes, it would be very interesting to understand this. So whether, certainly I believe that some of what I showed at maybe the second part, which was the effect of a graph, looking at dispersion of graphs, this certainly you can transpose this to North American situation, I'm sure would be true, but whether there is an effect of road would be extremely interesting. I think this is really something that asks for clarification. If one could prove that there is really an effect of roads along the roads, I think would be an extremely interesting and important development. But at the moment, it's hard to say whether they are or not, but that would be extremely interesting. I'm very happy to know about this.
Thank you.
Oh, hi, Henri.
Hi, Shigui.
Yeah, hi. Very nice talk. Thank you very much. Just wondering, because the classical Laplacian operator is very good to describe the local random walk. Right? But in your last part, you're talking about COVID-19. But COVID-19, as far as we know, I mean, the long distance travel probably contributes to the country to country or long distance spread, more significantly. For that kind of problems, maybe the non-local, the first part of your talk, the non-local may be more feasible, right? Or maybe the fractional Laplacian operators more, because that kind of distribution is a levy flight, right?
Yes,
the normal distribution.
Very, very important point you're raising again here. So for the model with roads, we have now a study written up with Rockjoff and Rossi, where we allow for non-local movement for integral movement. So jump with flight, jump operator if you want. So a certain non-local operator with a kernel on the road. So that's certainly applied, that certainly tells you something about the road. And we can draw conclusions which are, we can derive a number of precise quantitative conclusions of the same spirit. I didn't show that because I didn't have time for that, but we can derive quite a number of quantitative results from that also. This is not yet written completely. It should be out very soon, but that involves integral terms on the road. Now, the next problem would be to understand the effect of having both integral terms on the road and integral terms of a different kind inside the field. That's still further to be done, and of course would be, as you say, it would make a lot of sense for the modeling for COVID-19 and other pandemics. But I believe
you are considering that. Okay, yeah, considering.
Yeah, this moment, I'm not surprised.
Yeah, okay.
That's right. This is a very important point you're raising. Yes, absolutely.
Yeah, thank you.
Understanding the non-local effect. But you see, on the road, you can really understand. So it's interesting to mix, local diffusion in the field and diffusion where people come
in the road,
point and jump to another point.
Sure.
You can do that. That's
combination. Yeah.
Okay.
Well,
yeah, I was about to ask you, Deirdre.
Okay, so we run well over time, so I think we probably have to stop here, but thank you very much, Henri, for this really interesting lecture, and especially for the opportunity to see both the applications and the new mathematics coming together. So until we'll be restarting this colloquium series in the early fall, until then, I hope that everybody has a good summer and a restful summer and comes back enthusiastic to get to work again. And I just hope things are a lot better over the summer. So thank you, Henri.
Thank you for running this. It's really wonderful that you do that.
Thank you.
Thank you.
Enjoy your dinner, Henri.
Yes.
Okay.
Yeah. Too bad you cannot take me out for drinks now, but
yeah.
next time.